Riotee is a general-purpose development platform for battery-free devices that is both open source and commercially available. In this video, we're going to take a look at the hardware, software, and documentation and replicate the case study presented in our paper. Let's start with the hardware. The Riotee board is a user-friendly development board integrating key battery-free device components with an onboard programmer, push button, LEDs, a USB-C port, and expansion headers. This setup facilitates rapid prototype creation without soldering or breadboard wiring. The board's 2-pin headers expose signals for supply voltage, capacitor voltage, and 11 GPIO pins supporting I2C, SPI, and analog sensor applications. These headers allow connecting custom harvesters, storage capacitors, or peripherals, and are also used to connect the Riotee shields. The solar shield features 4 small solar panels and a 2-position sliding switch that connects none, 1, 3, or all 4 panels in parallel. This configuration allows easy experimentation with different harvesting currents under given ambient light conditions. The capacitor shield includes 8 capacitors of different values and dielectrics. An 8-position sliding switch enables selection from 256 possible capacitor combinations to meet application needs. It also helps users to observe the impact of energy storage size on system behavior. The sensor shield integrates an accelerometer, a digital temperature and humidity sensor, and an analog microphone with a power switch. The sensor shield enables quick assembly of real sensing applications and is used in some software examples and our hardware detection case study. This hardware is accompanied by an open source software development kit that includes a battery-free runtime, various peripheral drivers, and 2 network protocols. The SDK also contains a total of 18 examples ranging from a simple blinky to a more complex hardware detection application that we're going to walk through later. The code is thoroughly commented and the resulting API reference is combined with contextual documentation and rendered on a publicly available webpage. The effectiveness and usability of Riotee is demonstrated through the case study presented in section 6 of our paper. A battery-free device equipped with a microphone listens in low-power mode. Upon detecting a sound, the device wakes up and captures a 1-second audio sample at a 16 kHz sampling rate. After extracting features from the audio sample, the data are fed into a machine learning model designed to recognize and differentiate between 2 predefined keywords, yes and no. The outcome of the on-device classification is then sent to a smartphone. First, we prepare the hardware. On the capacitor shield, we move the sliding switches numbered 1 to 6 to the on position, while switches 7 and 8 remain in the off position. On the solar shield, we move both sliding switches to the on position. We stack the 4 boards on top of each other, bottom to top in the following order: Riotee board, capacitor shield, sensor shield, solar shield. Next, we install the required software, starting with the prerequisites. Following that, we install the Riotee probe utility and ensure that it is available on the path. Then we download the Riotee UDEF rules, copy them to the corresponding directory in our machine, and reload the UDEF rules. We close the current terminal, open a new terminal, and clone the SDK repository. We change into the directory of the microspeech example in the SDK and build the firmware. Next, we connect the USB cable between the USB-C port of the Riotee board and the USB port of the computer and flash the compiled firmware on the board. When flashing is done, we can disconnect the USB-C cable. We head over to our browser and download the Celia software. When the download has finished, we open the corresponding directory, mark the application image as executable, and start it. First, we set up our channels. Channel 0 will be a digital channel used for the UART output, and channel 1 is an analog channel showing the capacitor voltage. We also set up an async serial analyzer to decode the UART output from the device with a baud rate of 1 megasample per second. Now we can connect the probes. First, we connect the ground probe. Channel 0 goes to the pin TX labeled on the bottom of the Riotee board. And channel 1 goes to the pin labeled VCAP on the bottom of the Riotee board. Now we're ready to start the recording. Yes. After saying the hot word, we cover the panels for a while with our hand. Once the power goes off, we uncover the panels again. Now we wait until processing has finished. And stop the recording. Initially, the capacitor is fully charged while the device waits for a sound. Upon detection, sampling starts with medium power draw. Immediately after sampling, processing starts with higher power draw, quickly draining the remaining energy before execution is suspended until the capacitor is recharged. After covering the solar panels with a hand, the capacitor discharges slowly to around 2.5 volts. At this point, a 45 kilobyte checkpoint, including the audio sample, the processing buffer, and the application stack, is stored in non-volatile memory. Shortly after, the buck regulator switches off the supply voltage. Upon uncovering the solar panels, the capacitor quickly charges up, the supply voltage turns on, the MCU starts up, and processing continues. Once it's done, the result is output via UART. Let's have a look. Indeed, the device correctly detected the hot word yes with a 92% probability. Finally, this result is transmitted as a BLE packet, causing another small bump in the capacitor voltage.